Hello, this is Kelly Freeman with A+ College Ready, and I'm here to talk to you about scientific math. There are two types of data. One is quantitative. This type of data involves measurements and numbers. An example of quantitative data would be 620 nanometers of light. It's a measurement with a number. It's also qualitative data. This type of data involves description or narrative. So you might use the term red light to describe a type of light. It's descriptive. Accuracy is conforming to a correct value or standard, while precision is the ability to generate the same value repeatedly. Both are necessary if you want to have good results in a laboratory. The goal in your work is to be both accurate and precise. If you take a look at this diagram with the bullseye, you'll see if you hit the bullseye, which is the standard, that would be accurate. If you hit the same area over and over again, like this player did, you're very precise. You're doing the same thing wrong again and again, but you're not very accurate. You're not hitting the standard. In this situation, you are both accurate, you've hit the standard, and you're also precise. You're hitting that standard over and over again. Percent error is a mathematical equation that will help you give you a handle on how you're doing in the laboratory and how close you were to the accepted value. Percent error is used to determine how close your measured values are to your accepted value. So you take your measured or your experimental value that you got in the laboratory and you compare it to a standard value. So here's an example. A student determines or measures the density of a substance to be 1.400 grams per ml. So what this means is the student took some mass readings, measured some mass and measured some volume of a particular substance and calculated then the density. Find the percent error if the accepted value of the density is 1.360. This is the value you'd find in a reference chart. So you take your experimental or your measured value, put it here, you compare it, get the difference between your measured value and the accepted value, and then divide it by the accepted value again. So you try. A student calculates the density of iron as 6.80 grams per cubic centimeter by using lab data for mass and volume. A handbook reveals that the correct value is 7.86 grams per cubic centimeter. What's the percent error? So here you identify that this is the measured or experimental value. That's because this was done in the laboratory. Here is the accepted or the theoretical value that you would get out of a reference book. You take your experimental or measured value, compare it to your theoretical or accepted value, divide again by that theoretical or accepted value, and you get a 13.5. Percent error can be positive or negative. The number of digits that can be measured with certainty plus one additional digit that is estimated are significant figures. The function of significant figures is to maintain scientific integrity. Lab results should never be reported out as more certain than the least certain measurement in your calculations. The least certain measurement in your calculations. When we manipulate our data from the laboratory and put it in a calculator, sometimes we get a long string of digits. If we report out 10, 12 digits, it may appear to people who are reading our work that we actually measured out that far, that we actually had an instrument that measured out that far, when in reality, certainly in high school, we never have an instrument that can measure to that place past the decimal. So we have to be careful to report out lab results that are never they're never represented as more certain than the least certain measurement we took in the laboratory. This maintains scientific integrity. For example, this cylinder should be read as 44.9 mLs. We can read up to 44 mLs with certainty because the graduated cylinder is marked out in units of 1. But that last digit, this digit, is an estimated digit. The cylinder is not graduated into tenths, and so we have to make a guess. We have to make an estimate about this digit. So you try. Report out the volume measurement reading for the graduated cylinder to the proper significant figure. So the reading here would appropriately, in terms of significant figures, would be 63.5. We can read with certainty 63. The graduated cylinder is marked out in increments of 1, so we can read up to 63 with certainty. That place past the decimal, that 10th place, has to be estimated. It could be that someone else might call that a 4, or someone else might call that a 6. It wouldn't be wrong. This is an estimated digit. There are rules for zeros when we're looking at significant figures. All non-zero digits are significant. For example, 1.223 grams has 4 significant figures, all are non-zero digits. This numeral has 5 significant figures, all non-zero digits. Zeros between non-zero digits are significant. So this 0 between the 6 and the 8, between 2 non-zero digits, is significant. So we count all the non-zero digits plus the 0 for a total of 6 significant figures in this measurement. This measurement has 2 zeros between 2 non-zero digits. These 2 zeros, therefore, are significant. So this measurement has a total of 6 significant figures. This 0 is not significant. We'll talk about that in a moment. Zeros to the right of a non-zero digit are not significant. For example, 147,000 has 3 significant figures. Only the 3 non-zero digits are significant. Zeros to the right of the non-zero digits are not significant. 50 has only 1 significant figure. There is an exception to this rule. This number, even though it has a trailing 0, also has the decimal behind it. Let's try to get rid of that. I didn't mean to. Now. Okay. So that 0, because there is a decimal behind it, is significant. Therefore, this measurement has 4 significant figures. The decimal indicates that the person who made this measurement did measure out to this place. Zeros to the right of the decimal and to the left of a non-zero digit are not significant. So zeros to the right of the decimal and to the left of a non-zero digit are not significant. Therefore, these zeros are not significant. Therefore, this measurement has only 3 significant figures. This 0 is significant because it's between 2 non-zero digits. However, 0 to the right of the decimal and to the left of non-zero digits are not significant. This is not significant, neither is this 0. Zeros at the end of the number and to the right of a non-zero digit are significant. So this 0 is significant because it's between 2 non-zero digits, and the zeros to the right of the number and to the right of non-zero digits are significant. Therefore, the person who made these measurements carried out these numbers intentionally. They wanted you to know they did measure out that far. So this measurement has 6 significant figures. The 0 in front of the decimal is not significant. So let's practice. Take a look at these numbers and try to figure out how many significant figures each of these measurements has. This first measurement has a total of 6 significant figures because the zeros are to the right of non-zero digits and to the right of the decimal. These two zeros are significant. This measurement has 4 significant figures. The 0 between the 5 and the 9 is significant. This 0 is not significant. This measurement has 2 significant figures, the 2 non-zero digits. This measurement has 7 significant figures. The trailing zeros are not significant. There's no decimal at the end. So 1, 2, 3, 4, 5, 6, 7 digits are significant. This measurement has past the decimal, and to the front of non-zero digits, it has 3 zeros. These zeros are not significant. Therefore, only these 2 non-zero digits are significant. And finally, because this measurement has a decimal place at the end, it's the indication that all zeros should be significant in front of it. So this has a total of 5 significant figures. So in the laboratory, we often have to, after we take our measurements, we often have to add and subtract, multiply and divide when we manipulate them to find things like density or molarity or other important aspects that we need in order to carry out our lab work. So we need to review how to use significant figures, adding and subtracting the significant figures. Your sum or your difference may not be reported with more certainty than the least certain measurement that you made in the laboratory. When you're adding and subtracting, you should report out the answer so that it has no more digits to the right of the decimal than the measurement with the fewest digits to the right of the decimal. Then the measurement, it's the measurement that determines the significant figures. So we're going to look at the least certain measurement, EAST, least certain measurement. That will help us determine our significant figures for our answer. Here's an example. So suppose you've made 2 measurements in the laboratory, and this measurement was actually carried out to a more precise reading. You had an instrument that was able to read to the 100th place, while you used an instrument over here that was only able to read to the 10th place. When you add these 2 pieces of lab data into your calculator, you'll get an answer that looks like this. But that's really not reporting out with scientific integrity. The measurement 4.2 has not been measured with as much certainty as the 5.32 measurement. The answer must reflect the measurement with the least certainty. The measurement with the least certainty is this 4.2 measurement. Therefore, the answer should be rounded to reflect the least certain measurement, showing the same number of digits past the decimal point as the measurement with the fewest digits past the decimal point. 4.2 has 1 digit past the decimal point. 5.32 has 2. This is the less certain measurement. Therefore, your answer should reflect that. Multiplication and division using significant figures. This is another rule, an additional rule, slightly different from addition and subtraction. The answer may not be reported out with more certainty than the measurement with the least number of digits, certain digits. The answer should not be reported out to the number of significant figures in the least certain measurement. Let me try that again. The answer should be reported out to the number of significant figures in the least certain measurement. Here's an example. So we have two pieces of lab data here. One was made with an instrument that could read out to the 100th place, while one can only read out to the 10th place. This measurement is less certain compared to this measurement. And when you report out your results, you have to reflect that least certain reading. This has 2 significant figures, while this measurement has 3 significant figures. And the rule says you should report out to the least number of significant figures. Therefore, this calculator answer is too much, giving a wrong impression that you actually measured out to this 1000th place. You did not. You should report the answer out to 2 significant figures, and that should be your answer. So here's some practice. Make sure you follow the rules for addition and subtraction, and then also follow the rule for multiplication and division in terms of significant figures. So in my calculator, when I subtract 0.227 from 4.6678, I get a calculator answer of 4.4408. But I need to report out my answer using the measurement that has the fewest number of digits past the decimal. That would be this one. It has only 3 places past the decimal. Therefore, I need to report out to that 0 place, which is the 3rd place past the decimal. I have the 8 round the 0 up to a 1, and so in terms of significant figures, my answer should be 4.441. On the division problem, number 2 division problem, I have 5 significant figures in the top measurement and 3 significant figures in the bottom measurement. Therefore, I should report out to 3 significant figures. This is the place, this 1 is the place I should round to. The 9 rounds the 1 up, so I should report out to 3 significant figures. Remember, the trailing 0 is not significant. Number 3, I'm adding again, so I'm going to look at the number of digits past the decimal. This one has 1 digit past the decimal, this one has 4, this one has 2. So my answer should be reported out to 1 place past the decimal. This is what the calculator gave me. Here is my 1 place past the decimal. The 5 behind it rounds that 5 up, so that here is the answer I should report out. In the last example, I'm multiplying. This measurement has 3 significant figures. This measurement has 2 significant figures. Therefore, I should report out to the least certain measurement. That's the one with 2 significant figures. I want to round to that 2nd significant figure, that 1 there. The 8 rounds the 1 up, which gives me this answer. All the zeros past the 2 are not significant, so this answer also has 2 significant figures. Scientific notation is a way of expressing numbers that are too large or too small to be written conveniently as a decimal. Let's review some vocabulary. Actually, the vocabulary is on the other slide. This is just showing you the limits of scientific notation. That the coefficient itself, this is called the coefficient, has to be a number greater than or equal to 1 but less than 10. Has to be the rule for the coefficient. And b here, the exponent, has to be an integer. The number in front is called the coefficient. This number, raised on that power of 10, is called an exponent. You need to be able to convert decimals to scientific notation, and you need to go from scientific notation to decimals. So let's review the rules. If moving decimals to the right, your exponent will be more negative. So if I take this decimal and I move it until I have a number that is greater than 1 or equal to 1 and less than 10, I have to move that 3 places, right between the 7 and the 4. If I only move it 2 places, I have a number less than 1. which breaks the rules. If I move it 4 places, I have a number greater than 10, which would be 74.5. The only place where I have the proper number of 1 equal to or greater than 1 and less than 10 is if I move that decimal 3 places. If I'm moving to the right, my exponent will be more negative. I've moved it 3 places to the right, therefore my exponent will be a 3. Because I've moved it to the right, I have a negative exponent. Only significant figures are reported in scientific notation. If moving a decimal point to the left, your exponent will be more positive. So if I assume that the decimal is here, and I move it until I get a number equal to or greater than 1 and less than 10, I have to move it 5 places to get between the 4 and the 5. If I move it 1 less, I have 45. If I move it 1 more, I have 0.45. So 5 places is the only way I am able to obey the rule of equal to or greater than 1 and less than 10. I moved it 5 places, therefore my exponent will be 5, and it'll be positive because I've moved it to the left. You try. Express these numbers as scientific notation. So we're moving to the right, therefore our exponent is going to be negative 1, 2, 3. 1.245 times 10 to the negative 3. All of the significant figures are reported. Here I'm going to move to the left, so the number is going to be positive. 1, 2, 3, 4, 5. Also moved it between those 2 8s. That's 5 places, therefore my exponent is 5. Because I moved it to the left, it's positive. So let's now convert scientific notation to decimals. If you have a negative exponent, move the decimals as many places to the left as that exponent indicates. So I'm starting with 7.5. I have a negative 4 exponent. I'm going to move that decimal 4 places to the left. 1, 2, 3, 4. Decimal goes here. 1, 2, 3. And so my number will be . If you have a positive exponent, move the decimal as many places to the right as the exponent indicates. So I start with 4.5. I have an exponent of 5. I'm going to move that decimal 5 places then to the right. And 1, 2, 3, 4, 5. Replace it with the zeros, which gives me my answer. You try. Convert these numbers to decimals. So 7.02, I have a negative exponent, so I'm going to move it to the left 2 places. 1, 2, 0.0702. Here I have a positive exponent, so I'm going to move it to the right as many places as my exponent asks. 1, 2, 3, 4, giving me my answer. Frequently, you will be asked to answer mathematical test questions containing scientific notation without the use of a calculator. So it's really important that you learn how to do mental math with scientific notation. On the AP exam, you will not be allowed a calculator on the multiple choice section, so this is really critical in you being able to be successful on the exam. When you're adding and subtracting in scientific notation without the use of a calculator, you should get the exponents the same before adding or subtracting. So see here, we have 2 exponents that are different. We need to get these 2 exponents to be the same. So what we're going to do is we're going to take this decimal and we're going to move it 1 place to the left. Remember, if you move the decimal to the left, then you're going to increase, you're going to make that exponent more positive. So when we go to the left here and make it 0.60, this exponent goes from 2 to 3. Now our exponents are the same. This makes our math so much easier. So now we simply add these 2 coefficients together, and then we carry our exponent over. It gives us the answer. If moving the exponent to the left, if moving the exponent to the left, the exponent increases. Here we have an example. We're going to move this exponent to the left, just like we did here. As we move it, the exponent gets larger. Here we have a negative exponent. We're going to move that decimal to the left one place, and still again, the exponent gets larger, except this is a negative number, so it's moving towards 0. -1 is larger than -2. If moving the exponent to the right, the exponent decreases. I see, this should be decimal. So sorry. If moving the decimal to the right, if moving the decimal to the right. If moving the decimal to the right, then the exponent decreases. So here we have 6.0 times 10 to the second. I'm going to move that exponent to the right once. My decimal to the right, my exponent decreases. Here I have a negative exponent. I'm going to move it to the right once. I move it to the right, my exponent gets more negative or decreases. Once those exponents are the same, add or subtract the coefficients and keep the exponents. Remember to express your scientific notation in the proper significant figures. Once again, we've got exponents that are different. We're adding. So we're going to move the decimal in one of these numbers so that the exponents are the same. I've chosen to move this one to the left. That makes the exponent larger. Now we have 3 as the exponent in both of the values. Simply add up these two coefficients to get 5.90. Carry down the exponent. I have expressed it to the proper significant figures because I have 2 places past the decimal. Oh, excuse me, 1 place past the decimal here, 2 places past the decimal here, and so in reality, I should probably cross out that 0 so that we have 5.9 times 10 to the third. All right, you try some. All right, so let's practice some of these. So let's practice some of these. Here in A, we're going to make sure that our 2 exponents are the same. They are. So all we need to do is add these 2 coefficients. When I add the 2 coefficients, however, I get 11.75 times 10 to the 6th. That won't do. This number, if you remember, needs to be equal to or greater than 1 and less than 10. This is greater than 10. So I'm going to move this decimal over 1 place so that I have the proper number within my coefficient. When I move over to the left, that's going to make my exponent larger. So we're going from 6 to 7. I need to report out to the proper sig figs. I'm adding, so I have 2 places past the decimal in both of my measurements. I'm going to use the 7 to round the 5 up, so I'll report out to 1.16 times 10 to the 7th, and that is my answer. Let's do the next one. Some erase here. All right, let's look at B. In B, we have exponents that are different. So I need to get these exponents the same. I'm going to move this decimal over 1 place so that I have 0.31 times 10 to the, if I move to the left, my exponent increases, plus 4.87 times 10 to the 5th. Now, all I need to do is add these 2 numbers. When I add them together, I get 5.18. All I need to do is carry down my exponent, and that is my answer. Let's look at the next one. C. I notice again my two exponents are not the same, so I'm going to move this decimal over one place to the left so that I have 7.21 times 10 to the third plus 4.38 times 10 to the third. Moving to the left, the exponent increases. Now I simply add these two together for C. That gets me 11.59 times 10 to the third. All right, I'm in violation. So I need to take this exponent, move it over. I get 1.159 times 10 to the, I moved it over to the left, it increases, 10 to the fourth. I need to report out to the proper significant figures. This is C. I have two sig figs behind here, and when I moved it over, I have two sig figs here. I need to report out to two sig figs past the decimal. So 9 rounds of 5 up, 1.16 times 10 to the fourth is the answer. Let's look at the next one. This will be number 4. Here we have some negative exponents, and I notice they are not the same. So I want to use this. I'm going to move this decimal over to the left. That gets me 4.68 times 10 to the negative fifth, and I'm going to be adding 0.35 times 10 to the, if I moved it to the left, this increases. This is a negative number, so it's going to be negative fifth. Here my exponents are the same. I'm going to add the two numbers together. I get 5.03 times 10 to the negative fifth, and that is my answer. G. Here I have positive exponents again. They are not the same. So I'm going to move this one over to the left so that I'll have 9.87 times 10 to the fourth plus, minus 0.62 times 10 to the fourth. I'm going to add 9.87 and 0.62 together, and I get 9.25 times 10 to the fourth, and that is our answer. Oops. One more. Finally, I have two exponents that are not the same, and these are negative exponents. So I'm going to take this exponent, move it to the left. I'm going to make it larger. So I have 5.72 times 10 to the negative fourth minus 0.23 times 10 to, since this is a negative number, negative fourth is a larger number. Now my two exponents are the same. I'm going to subtract these two numbers, and I get 5.49 times 10 to the negative fourth. And that is my answer. Okay, let's talk about multiplication and division with scientific notation. When you're multiplying the scientific notation, you want to multiply the two coefficients together, but add the exponents, these two coefficients together, and add the exponents. So that 2 times 4 is 8, and then the two exponents add together end up being 6. When you're dividing, you want to divide the two coefficients. So 2 into 4 is 2, and you want to subtract the exponents, numerator minus denominator. My numerator is 2, my denominator is 4. That yields me a negative 2, and so the answer is 2 times 10 to the negative 2. So just to review, you want to multiply the coefficients and then add the exponents if you're having to multiply scientific notation. And when you're dividing, you want to subtract the exponents, numerator from denominator. This really shouldn't be numerator from denominator. It should be numerator minus denominator. So you want to take this 2 minus the 4. 2 minus 4 gets you a negative 2. That's going to be your exponent. All right, here's some examples for you to try. We'll go over them after you give them a shot. All right, so we're going to, this is multiplication. We're going to multiply these two coefficients together. And when you multiply them together, you get 9.6. You're going to add the two exponents, 9.6 times 10 to the 8th. And that is our answer. Once again, we're going to multiply these two coefficients. You get 9.99. Add the two exponents together. So a minus 4 plus a minus 5 gets you a minus 9, a negative 9. And that is the answer. Number 3 is also multiplication, so 1.2 times 1.5 gets us a 1.8. You're going to add those two exponents, a 6 plus a negative 7 gets us a negative 1, and that is the answer. All right, so now let's try some division. You want to divide the 4.21 into the 8.42. What we get is a 2.00 times 10 to. Now you want to subtract these two exponents. So it's going to be the numerator minus the denominator. That's going to give us 5, and that is the answer. Letter E, going to divide the two exponents. When I divide 2.4 into 8.3, I get 3.5 times 10 to 6 minus a negative 3 gets us a 6 plus a 3. That's going to be equal to 9. So the exponent is 9. And finally, our last one is also a division problem. I'm going to divide 1.1 into 3.3. It gets me a 3.0. I'm going to subtract the two exponents. So a minus 4 minus a negative 8 minus 4 plus a 6 gets us a 2. So that's going to be 3 times 10 to the 2nd. The SI system is probably something that you as a chemistry student have been exposed to many times. So we're going to treat this as a review. You do need to be familiar with the prefixes and what they mean and their relationship to the base unit. It's helpful to remember what's greater than the base unit and what's smaller than the base unit. Kilo and mega are both units that are greater than the base, so that there are 1,000, and kilo does mean 1,000, 1,000 meters in 1 kilometer. Centi and milli are both smaller units than the base, so that there are 100 centimeters, and that's what centi means, is 100 centimeters in 1 meter, and milli, which means 1,000, there's 1,000 millimeters in 1 meter. The SI system allows interchange between length and volume, which is something that the English system does not allow. A cubic centimeter is actually equal to 1 milliliter. So we're going from a length measurement to a volume measurement here, a length to a volume. So these conversion factors are handy to use when you are working with the SI system, if you need to go from length to volume or from volume to length. Also, a cubic decimeter is equal to 1 liter. So let's put this idea to use. We have a swimming pool here with the dimensions of 10 meters times 10 meters times 10 meters. So it'd be the length times the width times the height, or the depth if you want to think about a pool. And our question is, what's the volume in liters? So we have a length measurement and we're asked to go to a volume measurement. How are we going to do that? Well, we want to use a conversion factor between length and volume. We could use the cubic centimeter is equal to 1 ml, or we could use a cubic decimeter is equal to 1 liter. I'm choosing the centimeter because it gives us one more opportunity to do some metric conversion. So 1 meter times 100 centimeters over a meter, let me write this out a little more clear. So 1 meter times, for every 1 meter, I have 100 centimeters. Those meters cancel, and that gets me 100 centimeters. So in 1 meter, there are 100 centimeters. I'm going to find the volume. The volume would be equal to the length times the width times the height. So 100 times 100 times 100 gets us 1,000,000 centimeters cubed. So 1,000,000 centimeters cubed is equal to the same volume in milliliters, because 1 cubic centimeter is equal to 1 milliliter. And we know that 1,000 mLs is equal to 1 liter. So we're going to take those 1,000,000 milliliters, 2, 3, 4, 5, 6 mLs, and for every 1,000 mLs I get 1 liter. So those three match and those three cancel out, and it gives us 1,000 liters. Dimensional analysis is a problem-solving technique using known base units to solve for unknown variables. It's also known as a factor label method. Dimensional analysis problems must show the units. The units lead the problem solver to the solution of the problem. It's very important that you use units when you're doing dimensional analysis. So here's a sample problem. How many centimeters are in 244 meters? Step 1, you want to write the known equivalence, the conversion factor, between the two variables in the problem. So we wanted to know the relationship between meters and centimeters. Well, because centi means 100 and centimeters are smaller than meters, there are 100 centimeters in 1 meter. Once you've written your relationship, and I'm going to rewrite that up here, there are 100 centimeters is equal to 1 meter. You want to start with the given in the problem and include the unit. Place the variable from the conversion factor. Let's put it up here. 1,000 centimeters is equal to 1 meter. Place the variable from the conversion factor with the same unit in the bottom so that the units will cancel. Here I have meters. I'm going to go to my conversion factor and find the variable that has meters beside it. Here it is. I'm going to bring it to the bottom so that the meters are going to cancel out when you divide one into the other. Fourth step, place the equivalent value from the conversion factor on top. So I've taken my 1 meter, put it here. I knew to do that because I started with meters in the given. Then I'm going to take what that 1 meter is equal to, 100 centimeters, and I'm going to place it on top. The meters cancel, leaving you with the only unit that you were asked for. Multiply across the top, divide by the bottom number, and report out to the proper significant figures and express with the unit left. Once again, my meters cancel. It leaves me with centimeters. I'm going to multiply across. 244 times 100 divided by 1 is equal to 24,400 centimeters. I have 3 significant figures in my given. I have 3 significant figures in my answer. Some problems require more than one conversion factor. Let's talk about this problem. How many seconds are in 54.6 hours? Well, I've got to go from seconds to hours, or from hours to seconds. Now, there's not a direct, we could make one, but there's not a direct relationship between those hours and the seconds. We normally have to go through minutes. So I'm going to write the 2 relationships I know. I know that there are 60 seconds in 1 minute, and that there are 60 minutes in 1 hour. So now I have a way to get from hours to seconds. I'm going to start with the given. Here it is. Then I'm going to use my conversion factors that I've already written down. Whatever unit is here must go here. I'm going to go to my conversion factor. Here it is. And I'm going to pull it down to the bottom. I'm going to put what it's equal to on top. These units cancel. Now I'm gone to minutes. Whatever unit is here goes here. I'm going to go to the conversion factor and find that unit, minutes. I'm going to put the value down as 1. Then I'm going to put what it's equal to here on top. Minutes cancel. That leaves me with seconds. Seconds was what I was asked for. I'm going to multiply atop. I'm going to multiply on the bottom. I'm going to divide the bottom and the top, and that secures my answer. You try. All right, so let's work these out. How many milliliters are in 16.2 liters? Well, I'm first going to write the relationship between milliliters and liters. A milli means 1,000. Milli is smaller than a liter, so there must be 1,000 of the small ones in 1 of the large ones. Here's my conversion factor. There's where my thinking begins. I'm going to start with the given, 16.2 liters times whatever unit is here goes here. Go get the value for it. There it is. Bring it back down. Then I'm going to take what it's equal to, and I'm going to put it on top. My liters cancel. Multiply across the top, multiply across the bottom. Use the only unit that's left, and that gets me 16,200 mLs. 3 sig figs in the given, 3 sig figs in the answer. So let's try the next one. Get rid of all our little lines. How many kilograms are in 0.82 centigrams? So this doesn't have a direct equivalence. We're going to have to go through the base unit. So kilo means 1,000. So it's going to be 1,001. Kilograms are larger than grams, so there must be 1,000 grams, smaller unit, in 1 kilogram. Then I've got to get to centigrams, and centi means 100, and 1. Centi is a smaller unit than the base unit grams, so there must be 100 of the smaller ones in 1 of the larger ones. Now I have my conversion factors. I'm going to start with the given 0.82 centigrams times. Then I'm going to take whatever unit is here, and I'm going to put it on the bottom so that they cancel. I'm going to go to my conversion factor, find the value I need. Here it comes down. Then I'm going to take what it's equal to and put it on top. I have now canceled out the centigrams. But I'm just stuck grams, so now I've got to get to the kilograms. So, one more problem. Whatever is here goes here. Whatever is here goes here. So, grams. Go to the conversion factor and find the grams. Take the value, put it with the unit. Go back to the conversion factor, find what it's equal to, put it on top. Your units will cancel, leaving you with the units that you asked for in the first place. Multiply across the top, multiply across the bottom, divide the bottom and the top, and you get the answer. You have answer of 2 sig figs in the given, you have 2 sig figs in the answer. That is the correct answer. And one more. Okay, how many kilometers are in 2.6 times 10 to the 5th millimeters? Once again, that's not a direct correlation. We're going to have to go through the base unit. So kilo, I know kilo means 1,000. And kilos is larger than the base unit, so there must be 1,000 of the small and 1 of the large. Milli means also 1,000, but milli is smaller than the base unit, so there must be 1,000 of the smaller ones and 1 of the larger ones. There are my conversion factors. Let's start with the given. 2.6 times 10 to the 5th millimeters. Whatever unit is here goes here. Go to the conversion factor, find the unit, take the number that goes with it, bring it down and put it with the unit. Go back to the conversion factor. Whatever that was equal to, it goes on top, 1 meter. I've now gotten rid of the millimeters and I am to meters. One more step. Whatever unit is here goes here, meters. Go to the conversion factor and find the meters. Look at the number, put the number with the unit. Go back to the conversion factor, find what it's equal to, put that on top. Units cancel. Multiply across, divide the bottom into the top, and you end up with 0.26 millimeters. I have 2 significant figures in my given. I have 2 significant figures in my answer. Density is mass per unit volume. Density can be measured in many different metric units for mass, while volume can be measured in units of volume and also derived units of volume from the cubic centimeters, cubic decimeters, and other types of units from the metric system. So here's a theoretical question or thought experiment. Have 2 pieces of copper, one much smaller than the other. Which one of these pieces of copper has a greater density? Think about it. It's a trick question. They both have the same density. Density is an intensive value. It does not depend on the mass or the volume. The mass is directly proportional to the volume in terms of your density, mass over volume, meaning that as the volume increases, the mass increases also proportionally. When you graph this type of relationship, when you graph a directly proportional relationship, you get a straight line. As one variable increases, the other variable increases proportionally. So the quotient of these 2 variables yields a constant. The equation for this line is probably an equation you've seen before. This is the equation for the straight line. In this equation, mass is the independent variable. Mass will be on the y-axis. Volume is the dependent variable. Volume will be on the x-axis. And the change in y over the change in x is equal to the mass over the volume, which is equal to density. So the slope of this relationship is the density, A, slope. Let's work some density problems. Here's our first problem. I'm going to go ahead and just put up at the top here our formula for density. So density is equal to mass over volume. They want us to find the density. Density is equal to 37 grams divided by 1.7 mLs. Divide the bottom into the top, and I end up getting 21.76 grams per ml. But I only have two significant figures in both of my measurements, so I need to report out my density to two sig figs. Density would be equal to, here's the second significant figure, that 1. I'm going to use this 7 to round that 1 up to a 2. So the correct answer would be 22 grams per ml would be the density of that first problem. So let's look at the second problem. This time they gave us the density, but they want the mass. So I'm going to rearrange this equation so that I get mass on one side. I'm going to multiply out that denominator on one side. If I do it on that side, I have to do it on this side. So now I have a new equation. The mass is equal to the volume times the density. But right away I also notice another problem. I notice that this is liters while this is milliliters, and that's not going to work. I've got to get my units the same. So what I'm going to do is I'm going to change these liters to milliliters. So there are 1,000 milliliters in 1 liter. So if I have 1.0 liter times 1 liter over 1,000 mLs, my liters cancel. That's going to give me it's going to give me 1,000 milliliters. So now I can work my problem. I've got the equation. I've got my units all right. So here we go. Mass is equal to volume times density. Mass is equal to 1,000 milliliters. 2.70 grams per ml. mLs cancel. When I multiply this out, I get 2,700 grams. I have two sig figs in my answer. I have my least certain measurement is 2 sig figs. I should report out to 2 sig figs. Last problem. So in this problem, I'm solving for volume. They give me the density. And I notice right away that I have a problem in my units again. I've got kilograms here and grams here. So to make things easier, I'm going to go ahead and manipulate my problem to get volume on one side. And then I'm going to change these kilograms to grams. So I'm going to start with density is equal to mass over volume. And knowing that I've got to get the volume on one side. So I'm going to multiply my volume on both sides so that I get volume times density is equal to mass. And then I'm going to divide out my density so that now my volume is on one side by itself. So that gets me the equation of volume is equal to mass over density. Still got to take care of this kilogram problem. So I know that there are 1,000 grams in 1 kilogram. I have 1.7 kilograms. Whatever unit is here goes down here. Go to the conversion factor, find it, there it is. What it's equal to goes on top. Units cancel, so 1.7 times 1,000 is equal to 1,700 grams. So now I can substitute these 1,700 grams for my kilogram. So my mass is going to be 1,700 grams divided by my density, which is, 11.3 grams per ml. Now notice how the grams cancel and mLs are under two division signs, this one and this one. Therefore, the mLs are going to come up to the top, and our unit on our volume is going to be milliliters. So when I divide 11.3 into 1,700, I get 150 mLs. My mass has 2 sig figs. That's my least certain measurement. I report out to 2 sig figs, and that is my answer. Inversely proportional relationships are different from directly proportional. In terms of inversely proportional, as one variable increases, the other variable decreases. Later on, when you study gas laws, you'll find that as the pressure on a gas increases, the volume of that gas decreases. This is an inversely proportional relationship. When you multiply these two variables, the product is a constant. And when you graph these two variables, it gets you a hyperbola curve like this. This is a curve of an inversely proportional relationship.